In today's lesson, I would like to make some discussion to the exercises of communication systems past paper. This is number 1. During the transmission of a signal, attenuation occurs and noise is picked up. State what is meant by attenuation. Attenuation is the gradual decrease or loss in the power of a signal the further it travels. It is on page 317 in your physics textbook. Now, what is meant by noise? Noise itself is the random, unwanted signal that adds to and distorts a transmitted signal. It is written on page 315 in your physics textbook. By reference to AII, explain the advantage of the transmission of the signal in digital form rather than in analog form. Referring to this statement that the advantage of the transmission in digital form is by regeneration, noise can be removed from a digital signal. It is also on page 315. Now, we have here the part of an analog signal shown in figure 4.1. And then the signal is to be transmitted in digital form. The analog signal is sampled at frequency of 1 × 10⁻³ Hz using an analog to digital converter or ADC. And the ADC produces 4-bit numbers. You have a table, the times at which the analog signal is sampled. Now, for the digital number at time 3 millisecond, we want to underline the least significant bit or LSB. What is LSB? Least significant bit. It is the bit on the right hand side of a binary number. Yeah, the bit on the left hand side is called the most significant bit, MSB. So the least significant bit is on the right hand side of a binary number, so that will be this one. Now state the digital numbers corresponding to the sampling between time t 4 millisecond and time t equals 6 millisecond. So we have to see this. When time is 4 millisecond, the voltage is 8 millivolt. At time equals 5 millisecond, the voltage is 6.8 millivolts. And when time equals 6 millisecond, the voltage is 4.7 millivolts. So we have to convert them into binary numbers, digital numbers. So at time 4 seconds, the voltage is 8 millivolts. So divide 8 by 2. 4, the remainder is 0. 4 divided by 2 is 2, the remainder is 0. 2 divided by 2 is 1, the remainder is 0. So it is 1, 0, 0, 0. So it is 1, 0, 0, 0 in digital number. At time equals 5 seconds, the voltage is 6.8 millivolts. Because it hasn't reached 7 millivolts, we should always round it down. So we assume that this is 6 millivolts. So 6 divided by 2 equals 3, the remainder is 0. 3 divided by 2 is 1, the remainder is 0. And that's all. We have 1, 1, 0. Remember, we have to have 4 bits. So we have to add 0, 1, 1, 0. At time equals 6 seconds, the voltage is 4.7 millivolts. Remember, once again, we have to round it down. So we have 4 millivolts divided by 2 equals 2. The remainder is 0. 2 divided by 2 is 1. The remainder is 0. So we have 1, 0, 0. But we have to have 4 bits. So we have 0, 1, 0, 0. Yeah, so if we want to complete this table, I have here 1, 0, 0, 0. Here 0, 1, 1, 0, and here 0, 1, 0, 0. Now The transmitted digital signal is converted back to an analog signal using a digital to analog converter or DAC. On figure 4.3, show the variation with time t of the output levels of the DAC from time 0 to 4 milliseconds. Assume that there is negligible time delay in the transmission line. So we are given this. So first we have to, I'd like to make a table that when time equals 0, the output level will be time equals 0, the output level will be 2 millivolts. When time equals 1, the output level will be 6 millivolts. When time equals 2, it will be 4 millivolts, the output. At time equals 3, it will be 5 millivolts. Yeah, at time equals 4, I don't think we will draw it, but at time equals 4 millisecond, the signal voltage will be 8 millivolts. Yeah, so I have time 0, the time and the output level table, so I can draw here that when the time is 0, the output level is 2 millivolts. At time equals 1, it will be 6 millivolts. At time equals 2, it will be 4 millivolts. At times equals 3, 5 millivolts. That's all, I guess. Now number 2, this is what we have answered. State what is meant by the attenuation of a signal. Once again, it's on page 317. Now, a transmission cable has a length of 30 kilometers and the attenuation per unit length of the cable is 24 decibels per kilometers. Calculate for a signal being transmitted along the cable the total attenuation in decibels. We'll just have to multiply the 30 kilometers by 2.4 decibels per kilometers. It will be equal to 72 decibels. That is the total attenuation in 30 kilometers. Because there is the loss of signal, 2.4 decibels every kilometer. So if we have 30 kilometers, then the total attenuation will be 72 decibels. We want to find now the ratio of the input power of signal and the output power of signal. We can use the equation of attenuation, which is 10 times the log of P out over P in. And of course, we should give the attenuation negative sign. Or if we want to directly find the input power over the output power, then we can use this equation. Decibel, positive value, equals 10 times the log of P in over P out. So I have 72 equals 10 times the log of P in over P out. That's how I calculated P in over P out is equal to 1.58 something times 10 to the 7 or 1.6 times 10 to the 7 without unit because this is a ratio. By reference to your answers in B, suggest why the attenuation of transmitted signals is usually expressed in decibels. It is for a reason that smaller numbers can be used, thus it is more manageable. I would like to add one more question to be discussed. I have figure 10.1, shows the variation with frequency f of the power p of a radio signal. And we want to state the name of the type of modulation of this radio signal. When you have this type of variation of frequency, then the type of modulation will be the amplitude modulation or AM. Now you have to state the name of the component of frequency 50 kilohertz, this one. This one is called the carrier frequency. Yeah, so this is the carrier frequency and those are the sidebands frequency. This one is the lower sideband and that one is the upper sideband. So for the next question, the components of frequencies 45 kilohertz and 55 kilohertz, they are called the sideband frequencies. Now, state the bandwidth of the radio signal. We know that the bandwidth is equal to the upper sideband minus the lower sideband. It is equal to 55 minus 45. It is equal to 10 kilohertz. Next question, on the axis on figure below, we want to sketch a graph to show the variation with time t of the signal voltage of figure 10.1. In this case, we have two types of frequencies. The frequency of the modulating waveform is given from the bandwidth. We can see before that the bandwidth is 10 kilohertz. That is twice the frequency of the modulating waveform. So the modulating waveform will have the frequency of 5 kilohertz. That's why the period is 1 over 5 kilohertz. So it will be 200 microsecond. That is the period of the modulating waveform. And the period of the carrier waveform itself, we should calculate from here. The component of frequency 50 kilohertz, that means that the period is 1 over 50,000 hertz, and that will give us 20 microsecond. So the graph will be like this. Like this. We have the period of the carrier waveform, 20 microsecond. Period is the time to do one wave. And then for the modulating waveform, the period will be 200 microsecond, the time to do one wave. That's the graph. Okay, that's all. Now you have to do yourself the past paper questions that I give you. Exercise 2, number 1 has been done for you. You'll just have to try it yourself. And then exercise 3 will be given tomorrow, and it will be submitted. So please do your best individually so that you understand this chapter. Next week, I will give you AS level past paper reviews to prepare for the AS level mock exams that will be coming maybe the next 2 weeks. The schedule will be given later. Okay, I hope this video is useful for you. If you have any questions, you can contact me. Thank you.